So hello everyone. Hopefully you've been enjoying the show on this second day, and I've chatted with a few of you, and I hope to talk with more of you after this section. So welcome to the ARC306 session. If you could, it looks like we're pretty good on chairs, so no need to compress. I want to talk to you today about the fact that most of us here have probably been involved in a variety of creation about unique solutions, maybe for unique things. And if you haven't, maybe you're interested in creating those unique solutions with unique things, or maybe you're in yesterday's hack day. But today, actually, we're going to talk about the challenges and the way that the cloud actually meets those challenges of a small thing. So at the end of this session, there will be an architecture diagram that actually gathers together all of the known challenges today and gives you a single perspective on how to address those by leveraging the cloud. So I'm Brett Francis. I'm a solutions architect at AWS, and let's explore. Give me this. So as a first example, if you have a smart watch or some wearable or something of that nature, or clothing maybe that has telemetry built into it, you have a small thing. So maybe you're sitting here because you haven't started building those devices yet, and the question is, how do you build them? And then more importantly, how do you actually address them when they scale? So today, how do you survive and seek answers to your success is one way of thinking about the challenges that we're going to explore. So then, instead of asking the question, what is a small thing, I propose you actually want to change the question of why is a small thing a valuable tool for the job. So a small thing actually often is valuable because it maximizes the resource that it is limited by using it as little as possible. So let's actually define then what resource-constrained devices are. So a resource-constrained device actually is something that is constrained in one of the many compute dimensions. This could be network, it could be storage, it could be power, it could be actually a human interface. Often these things are deployed commonly at scale. They might start at the hundreds or one, but as you succeed, they can get into the hundreds of thousands or even millions. They can be global in footprint from a solutions perspective, and they often have a non-zero amount of compute inside of them. So just as a quick aside, there's going to be some later slides where I refer to sensors. So I'm going to be defining sensors today for this talk as something with no compute. So not resource constrained, but the absence of compute in that. So then, since you're sitting here, you are also probably aware that the phrase, the Internet of Things, is a highly overloaded phrase. So I wanted to go into that a bit and carve out a section of what I'm actually talking about today with a small thing. So instead of the open-ended term, we're going to go through a few of these. So today, Internet of Things covers mobile devices and maker devices. It covers unfamiliar devices and some familiar devices, such as something embedded in your body. It also covers large devices that might have multiple computers that are sending telemetry, or a, quote, small device, such as an intelligent tractor. Additionally, it could be big devices, such as this massive power capability, or it could also be something physically small, like a microinverter, that is also generating power. So whether you're creating devices that are similar to these examples, or you want to actually create the next best smart coffee mug, the fact of the matter is the limitations of the device are what force you to focus on it as a small thing. So the moment you've entered the realm of thinking of the limitations of the device, you're starting to touch on this subsection of the Internet of Things that we're going to explore the architecture about. So with that breadth of the IoT term, slicing in and taking this small thing, when you have a small thing, it's ultimately connected, but it might actually need to be, oops, what happened? Okay, cool. It's actually connected, But everywhere that device might have a limitation, if you think of it as having a gap, then everywhere those gaps exist, actually a globally accessible cloud platform actually is in a good position to help fill those gaps. But the smaller the device is, the bigger the data, and actually, even though there's a lot of good tools out there already, there's still new challenges to address. So let's explore a bit. If you think of your challenges as creating a device and approaching that device as having gaps in it because of the resource constraints that you're exploring, then you're actually starting to get into the posture of how you might leverage the cloud to fill in those gaps specifically. The first challenge actually I want to go into that is addressable when you leverage the cloud is the concept of telemetry. So for today's discussion, I'm going to be defining telemetry as the ability to remotely determine what a device senses. So given that, there's a common misconception, having worked with multiple customers in this space, taking that opening requirement and saying, it's just all I want to do is gather the sensor data and put it in. So there ends up this situation, we're going to talk through right now, that customers find themselves, if they just take that requirement and they start running with it, there's some pieces you might run into, if you will. Some challenges that almost always show up as heading down that path. So when actually those misconceptions are started, an architecture diagram looks like this. Multiple customers have thought of this in different ways, but at a very high level, you can think of the problem of telemetry for small things as being addressed by a picture that looks like this. So the stream in this picture, it could be a relational database, could be a NoSQL store, it could be an actual stream processing solution, a variety out there. It could often have HTTP or HTTPS in the mix, and that data is coming in over the HTTP and HTTPS into the stream. But what actually starts happening when this architecture gets into the real world is it struggles a bit. What should the device do if it just can't send the data in? How do you actually gather data and send it in if HTTP or HTTPS is just too heavy? The compute on the device just can't handle it. How do you address the challenge of a global solution? You have millions of these in a single infrastructure where you might have flocking behavior that comes about. I'll explore that in a second. How can a solution provide local endpoints? So you might have devices in North America that you want to not have to traverse all the way over to Europe, or vice versa, but still end up with a global perspective on your fleet, on all of the devices that are out there. Another way of thinking of a challenge that's in this space is often in the realm of telemetry, you start very small. There's a few devices, they start communicating, there's more, we start succeeding just a little bit, and then really we start going off the edge of success. And when you have this many things on the planet and success starts looking like thousands or millions of things out there all having common behaviors, the last thing you want is for that global fleet to act like a flock. You don't want coordinated behaviors as much as you can. So then minimizing those coordinated behaviors becomes a key architectural constraint that allows you to grow and still scale. It also allows you to minimize the waves and the crests, the wave crests and the troughs that are in any inadvertent organized behavior, so that your solution costs can be kept at a minimum as well. So what you then need in the real world with telemetry often is some strategies to overcome intermittent connectivity. I mentioned earlier, what if you can't just send it in? You need some strategies for reliably sending data in. Also, you need an elastic response by the solution itself. There's always situations where there are devices that do coordinate their behavior. And then you need an offline recording data strategy as well. So for those situations where the small thing is out there and it truly just can't send it in. So network communications is always intermittent. We've all been experiencing that as long as we've been on the network. But with small things, it's actually even more intermittent. They end up in environments that could be hostile or not. They might be transient, they might be moving. So then when a device is actually sending telemetry in, logging algorithms start to matter. So the way that device records information locally before sending it becomes an important topic to consider. So all of these algorithms are off of the cloud. So these have nothing to do with the cloud itself. But by starting to think about these, what you're doing is you're introducing little drops of scale to fill in those gaps that are out in the devices themselves. We've seen customers leverage FIFO. It tends to be a very simple, straightforward one. Things arrive at the left and they go off at the right when they run out of space. But there's two other algorithms I would want to put into your heads as you're exploring small things and how they might be created. And those are aggregate and culling algorithms. So these algorithms, they tend to be a little more complex, but they provide some different benefit in that they might actually fit better with the data that's being reported because of the lossiness of the granularity or the history that you might need. So these three algorithms become a key tool for a larger global solution because they allow you to at least first locally with the device address what happens if you can't just send information in for a telemetry solution. So then, another area that should be explored, and this does start traversing from the small thing over to the cloud itself, is when network computing and power are low, there's other protocols out there. There are protocols such as MQTT, CoAP, if I remember correctly, a variety of machine-to-machine protocols that exist, and these protocols actually might help depending on the capabilities of your device. So one common benefit here that you could explore is, since you have a cloud, you could actually have different endpoints for different modes of a device. So a pattern that I've seen succeed is you might use HTTP or HTTPS to get your configuration data from some back-end solution, but then the device goes into a low heartbeat mode until it has telemetry to send, and it sends that consistently, reliably over a lower resource or lower compute required protocol, such as the machine-to-machine ones that are out there. So that split mode interaction of separating your configuration or the things that happen intermittently but might operate in a high power mode of your device with things that happen all the time, which are going to be a perpetual drain on power or the bandwidth you might be limited by, is a pattern that actually I would suggest you're going to want to explore. So then, taking the original basic diagram I had here earlier that was just jumping into the requirement as was stated, but now adding some of this real-world exposure, the trickle starts to become a stream. So it actually starts to become this reliable stream where the machine-to-machine brokers acting as a proxy to that stream allow the devices to still communicate reliably. The logging algorithms on the devices allow you to overcome the intermittent nature of the world. And then that basic HTTP diagram starts looking such as this evolved telemetry perspective. But what if you have devices across the globe? So eventually those streams you're going to want to flow into a river. So if you have a diagram such as this, and you take the basic diagram and actually put it alongside the evolved diagram, what you then have at the top left is an infrastructure that might perfectly leverage HTTP and HTTPS. This architecture then separates that off, just in this diagram, as a regional approach. Then you have in the lower left, you have a proxied flavor as well. That flavor then is in another region. So what does this actually then do is that even if there's bad behavior in your things, there's never a global flock behavior going into your larger solution. So you can subdivide your regional behaviors by protocol or by generation of device, These regional streams still, however, can flow into a centralized stream for the common analytics and correlation perspective you might seek. So, stepping back to the beginning, when I mentioned that even though there are small things out there, they result in big data over time, you can see that even if there were 1 million small things on the planet and you were building something, customers growing such a fleet as that, even if they're sending a few bytes a day, when you start growing this across the globe, you end up in a big data realm. So joining those streams into this river is not the topic today, but we are having many topics on big data. But today we're going to keep focused on the architectural patterns right there with that small thing. But I wanted to point out that even though they are small, even though they are not the mobile device that has a ton of compute in it and 64-bit processing, they still add up over time to something you're going to want to consider as a big data problem as you scale your system. So then taking that original picture of the gap-oriented approach, then where a global cloud platform actually fills in some of those gaps is the global ubiquity of the cloud itself actually allows these regional behaviors of these small things. It splits the flock, ultimately. The elasticity of a solution then allows you to overcome any peaks and valleys, or crests and troughs in the flow. The ability to actually have zero-cost inbound data transfer goes a long way to allowing a small thing to exist in and of itself. So the cost profile of a small thing to get even a few bytes of communication or a few kilobytes of communication, the last thing you want is another charge on that when the data arrives on the other end of the telemetry flow. So can't underestimate that. So, and then last but not least, I've seen many interesting applications out in the space already where the benefit of the purpose-built service actually keeps another dimension of cost really low to allow the fleet to scale to massive dimensions, and that's the purpose-built services. They actually keep your headline, well, headline actually is right, your salary line and your head count at a relatively focused cost, because then you're not having to manage these entire fleets of infrastructure in addition to the fleet of things that are out in the world. So, but there's still some gaps. So let's explore a bit more. So now that we can actually send device information in, maybe we want to send commands back out to them. So how would you do that? Today, I'm going to define commands in this space as the ability to ask a device to do something. So then again, different customers have approached this in different ways, but I would sum it up as there's a common first step that a lot of them take. At the first day, when somebody comes across and asks that developer to create a command infrastructure, there's a common misconception that if I get it in your heads today and you just skip it, fantastic. I've helped a bunch of you. And that is that, well, we're just going to tell the devices to do something. It's as simple as that, right? It's just sending some outbound information. If I have inbound taken care of, outbound's taken care of too. Taking that and running with it, then customers will often make a picture that is in their heads or in their infrastructure that looks like this. Step one, the small thing requests some configuration or information about where it should go get commands. Step two, it takes that config and it goes gets the commands. It then executes those and does whatever it was supposed to do. So that being said, this architecture too starts suffering a bit when it gets into the real world. What happens when you're supposed to retry? What are the policies actually of the commands retrying? I mentioned earlier the global flocking behavior. How do you manage some of that? How do you know if it actually succeeded in a picture like this? And last but not least, what if your command has to go through an approval process? What if the device in play actually is something that has life-threatening capabilities with it? So these aspects are often things that are discovered as the devices and the small things start making their way past the proof of concept and out into the world. So if you can skip those steps, it'll be great. Putting this simply, sending the correct command matters. So there is a step. The ability to actually send reliable and correct commands is a step worth focusing on. So the fact of the matter is when you have hundreds of thousands of devices that are out in the world, the need to deliver synchronous and asynchronous interactions with those becomes a driving force. The ability to actually do that with minimal connections. So there's sometimes a device might end up in an environment where connection traversal over a network is purposefully kept at a minimum, sensitive information or sensitive environments. And then important commands, commands that actually are supposed to do something that is above the norm, actually should be more transactional in nature as well. So what's nice is there's some simple steps that actually can be taken to address this. So the simplest addition you can do in either of the pictures. So if on the left you have an approach where you're leveraging maybe a high-heat NoSQL database, or on the right where you're leveraging a machine-to-machine proxy fleet, the addition of a third step, even if all that step communicates is success, and the absence of communication implies failure, still gives you a lot of power and a lot of capability as you grow. The fact here is that when you're actually using a high-heat NoSQL database, you can actually imagine this being done with a single connection as well. So you can have a connection, a TCP connection open, and then asking for different fields to be edited on that at different periods of time. But you keep it open to your solution. This also then allows for a fast async behavior in both of these patterns, so that even though the desire is to offer the small thing, the users of the small thing, the appearance of synchronous interaction, it's really fast async under the covers. You're using some common mediator between the humans in this system and the devices in the system. So that actually, so taking an actually deeper dive into the high heat picture, and just because I needed more space, focusing on the NoSQL perspective of this, if you were to add Cognito into the mix for supporting of your mobile devices or your users that are out in the world, and they then are authorized to get and to determine the pair of devices. So you have your mobile device that the user is associated with, and through that Cognito authorization, management of your mobile fleet, you're then determining which devices in the world you should associate with that mobile device. And then, after that, you execute the command. That, paired with the ability to determine success, allows you to have an asynchronous interaction with your fleet, but at the same time, this could be as fast as you choose to allow it to be. So you can choke this or unchoke this at your scale of your devices, ultimately what you want to pay for the elasticity or the non-elasticity of your fleet. So then, taking back to the picture again, so when you have commands, you notice they're the same arrows filling the space, but they actually fill them in different ways when you have commands in the mix. So now with global ubiquity, the benefit is that the regional command endpoints allow you to reduce the network intermittency between those devices. The elasticity of the system allows your users actually to come and go with the fleet. The introduction of Cognito in the mix allows you to have identity as a service, so it's another managed offering, so you don't have to worry about the scale of your users alongside the scale of your fleet of devices. But there's still some gaps here in the mix that need some help. So there's one other topic I want to go into, and then we're going to wrap up with fourth architectural piece. So now that we've got telemetry and commands, instead of just taking those and running with them, we want to ask, what might we have those devices do? So for today's discussion, actually I'm going to be using device DevOps as a phrase that I'm defining as the ability to ask a device, a small thing, to be something new. So this, too, has a common misconception that arises when implemented. Customers often take that as, well, then I'm just going to send out firmware updates when I need to, right? So if the thing can handle it, that's something that is often just a statement, and people start running and going and implementing proofs of concept as well. So when they take this and put it into a diagram, those customers then will run into some challenges as well. So step one here is we're riffing off of the command capability, and we've now received the command get firmware update. So step two here is once the small thing is given the command get firmware update, then it goes over to its location, maybe an object store, and obtains that firmware and then downloads it and does something. So here too, the real world introduces challenges that we've seen many customers struggle through. Those can be summarized as what if the fleet upgrades its coordination? What if you accidentally or purposefully send out a command to update all of your devices right now? What happens here too when you have a failed upgrade? Can the device actually recover? If it's in recover mode, how do you go about doing that? Should the bundles themselves be encrypted? Maybe that's your key intellectual property, is the software that's in there. So the ability to offer up encrypted bundles to your fleet becomes a key requirement as well. And then are there two classes of device that actually might be out in the world? Those that can upgrade themselves and those that can't. So because small things are often used in environments where humans possibly are not expected to interact, or they're not, but they really should be, because that's the way you could deliver the best customer experience, is to assume that if you kill it, it's dead. I propose that the best customer-centric approach you can take is to take this to heart and introduce something around DevOps with your device or your device fleet. So when you have hundreds of thousands, or again, millions of devices that are all displaying and applying additions, you need to, displaying or interacting with your device DevOps infrastructure, you need to have an ability to identify exceptions in the fleet. You also need to have an ability to do staged and rolling updates, so specific flavors of maybe commands. We'll get to here in a second. And the reason you want staged and rolling updates, again, is this wave behavior that shows up when you get large fleets of devices. So then to meet the real-world needs, we start again. We're going to layer in here the ability of the previous conversation about commands, and we're going to add the supporting tools of some process. So let's start actually by updating this with step 3 at the bottom. There we go. So introduction of a staging environment is a key consideration for device DevOps. So, and in this staging environment, you're going to want a fleet of your things to be representative of what actually your world implies. So this often implies multiple generations running at any point in time. It also often implies the ability to have multiple firmware applications running on these things at the simultaneous system as well. You want to have in a perspective here that's very familiar then to the DevOps flows that we've used in other domains. And this is, so if you have your fleet that is running through the ability to update itself on the right in the staging environment. So let's say you apply this get firmware update to that environment, and they all succeed, or enough of them succeed, that you get to the perspective that your bundle has been validated. So you're in the bottom right in this picture. So then you're in step A of the device DevOps flow. So in this case, you could automate it, or you could have a human do it. You would then copy that bundle from your staging environment, just like you would for websites, etc. You could then copy it over to your production environment, and then introduce the ability to have rolling commands out to your fleet. So instead of sending one command of update everything, then you apply the command by device or by batch of device. So then over the period of days, maybe, or hours, depending on how aggressive you want to upgrade your fleet, you can then wait for the application of those devices, firmware to themselves, and then the posting back of success. So then this gets into the last step, which is the D step on this picture, way down on the lower left, where you can start managing exceptions. So if you've rolled out 1 million devices, 10 of them just never got back, at this point, the policy is something that starts taking precedence. What do? Do you just do it again? Do you send the upgrade command again? Do you, if it's a power plant, do you send a person out there? So it depends on the thing, but the pattern is actually very similar because of the resource-constrained considerations that are in the mix. So then, again, some of these are filled the same way, but they're actually different benefits. So here, when you have bundles that are available from a globally available object store, you can see that there at the bottom. That's now been a new one that's filled in. The global ubiquity here also enables the segmentation of your production rollouts. So in addition to dividing your fleet command by command, you can actually divide it by continent if you're leveraging multiple streams across the globe. Leveraging staging environments is often a place where dev test really shines with the elasticity of the cloud. The last thing you want to do is pay for your staging fleet when nobody's actually developing anything. So the ability to stand that up and tear it down, or stand it up and reduce it drastically, is very valuable, but it still gets you the benefit of testing your applications and your rollouts of firmware or other important bundles to your fleet before you actually roll them out. But there's still some gaps in this mix. So the last challenge is audit and authorization. So for today, I'm going to be defining these as the ability to determine if the device should do something and should be something, if you really want to get into that too. Different customers here have also run in and approach this in a very different perspectives, but one summary of this is, well, I'm just going to allow the right devices to do something. That turns out to be a little more difficult. So what does the picture often look like? So the running in picture looks like this. Step 1, put the creds on the device. Step 2, use those credentials to authenticate and be authorized to perform some privilege. Based on those privileges, register itself, and then once registered, start doing something. Often it's telemetry at this point in time. The device itself starts sending information about itself, or if it's a command-only approach, it might be receiving commands in that situation. But again, this starts suffering in the real world. The challenge that arises is, could you actually bootstrap without putting credentials on the device? What if the device gets compromised? How do you actually know that? And more importantly, how do you avoid it in the first place? And then, should the actual approval of the device registering and acquiring different level of privilege go through itself an approval process? Is that something that you want humans to be in the mix? Maybe it's not good that the device just comes up, registers, and immediately starts doing something. Those classes of challenge in the audit and authorization space are different when you're in the resource-constrained perspective. So when you have hundreds and thousands of devices, again, keep saying that, exception management becomes a key. The ability to apply analysis across your fleet of what is going on at this point in time. The ability to actually have a staged onboarding capability with resource-constrained devices becomes a challenge. The need to then have the human approval in the mix introduces some human-involved challenges themselves, but specifically they're around authorization of the addition of the device to the fleet. But the picture actually changes relatively simply by flipping it around. So instead of putting the credentials on the device in the first place, the device reports in some capability, some aspect about itself. So you might not be familiar with Cognito, it's a relatively new service, but there's an ability for it to give you unauthenticated privileges. So if you're the small thing, you can send in information about the AWS account. You can send in information about the pool ID that you're related to, the Cognito pool ID, and then maybe some unique characteristic of yourself, your CPU serial number, or some other attribute that might be truly unique to that device on the planet. Given this, these three pieces, because they're not credentials, these three pieces of information, then Cognito can offer you a Cognito ID that gives you access to an unauthenticated privilege set. So then, if you have an unauthenticated privilege of register and register alone, then that device can stay in that mode until a separate process takes place with the humans in the mix, or some other analysis, analytics, if you want to do automatic registration, or sorry, automatic approval of registrations. You could do that as well. But specifically, to acquire that last full privilege is a separate step. That full privilege does not come with the credentials that are being placed on the device. It is held off of the device and is managed through a process that is either automated or implemented by humans for purposes. So the key there is flipping that around in the first place. So these static credentials are now off the device. You've got users in the mix. You might have a web app that's there. And you've now bootstrapped this whole process in a very different way. So now, since Cognito itself can scale to the realm already of millions of devices, that's what it's designed to do, you've now gotten away with very resource-constrained environment. The device only needs to know something it already possesses, some characteristic of itself. So you don't even need to put anything on it. So you've got the least use of resources it could ever do. And now you still have audit and authorization in the mix in a highly controlled fashion. So with this and the addition of this Cognito perspective into the small thing space, you've now got all the currently identified gaps filled. So the suite of services you have here then are providing a capability that you couldn't have done by yourself. The device itself often might have previously had to do all this itself, but now you can leverage the cloud to fill these gaps in. So now, remember that diagram I mentioned in the beginning where there's one perspective that actually can bring all this together? So if you take all of these different architectures and you bring them together, you can actually think of them as addressing those small thing challenges and placing them into a cohesive picture. So just as an aside, for any of you that are familiar with the Lambda architecture, you might notice some similarities because there's actually an overlap in this picture, but we can talk about that after for anybody who wants to. But this is specifically about helping the device itself walk the trek up to being a source and up to fitting into a larger solution. So this Pragma architecture, Pragma stands for thing in Greek, this Pragma architecture has an intermittent layer. The intermittent layer acts as the control point for the speed layer. The intermittent layer also acts as the point for fleet management, and it supports high heat data. In this point, you're going to want something that can be as high heat as it needs to be, because that allows you to have the dual mode interaction that you might want as you scale. There's also a speed layer. So the speed layer here acts inbound as a high bandwidth data flow, and then outbound it acts as a command infrastructure. Depending on the flavor of device, it's not safe to assume that the inbound flow is always the big thing and the commands are the smaller thing. In fact, there are some out there that it goes the opposite, right? Depending on how much interaction is going on with these devices. But categorically, those two things still fit in actually with a very similar pattern in this one space, in this larger perspective. So then the serving layer enables the applications that your users or your other systems might want to leverage against your global fleet. So this serving layer takes advantage of the analysis and the correlation. It takes advantage of the ability to do real-time views from your speed layer. The serving layer also interacts with the intermittent layer to do controlled updates, and it acts as a source for human-driven commands. So I've mentioned a lot of human parts in this. Your serving layer supports those. So last but not least, there's a lot of customers that are already started on this, but I'm assuming that if you're here, maybe you're interested in starting too. So where might you actually get started? There's I'll call your attention to the second bullet first. There's an IoT mini site that's now out there. So on theme with the life sciences and many other domains we have, there's now an IoT mini site. Cognito itself, Kinesis, and DynamoDB become very valuable tools when scaling. One key point here is that even though I've gone through all of these different challenges, each thing is going to drive which one actually matters. So in the picture, the Pragma architecture, you don't have to implement the whole thing. The reason I'm bringing it up today is because often what happens is when you're implementing one facet and it grows and you succeed with it, the other facets start arriving over time. So to give you the perspective of how these things fit before you end up in tight spots or before you already have 1 million of them out there is my hope for what I was offering up in this segment today. So I want to thank you for being here. I'm going to be outside after this if anybody wants to talk, and I'm going to be at the dev lounge in about 20 minutes. So thank you very much.